Yeah.
Yeah.
All right, cool. All right. Hey, everybody. Welcome to another episode of Robo Papers. Super happy to finally get this chance to talk to Baoxiong, who is the co-author of two papers, which we'll kind of go through today with us. One of them is called COLA, so Learning Human-Humanoid Coordination for Collaborative Object Carrying. And then the other paper called UniFP, which is Learning a Unified Policy for Precision and Force Control in Liquid Loco-Manipulation. And in the case of the UniFP paper, these guys actually won the best paper award at Coral. So congrats on that.
Yeah.
I'm very happy for you guys. So maybe as a start, Baoxiong, if you can share a little bit about yourself before you go through your presentation.
Yeah. So I'll just start sharing. I myself, I did my bachelor's in Peking University in China and also PhD in at UCLA. I'm now a research scientist at Big AI, working on mostly embodied AI and also humanoids, and a little bit about 3D vision language learning. So if that's okay, we can start on the actual content. So I guess the major motivation was like when we had our first like unitary robots, we tried to play something with the robot because we are vision guys back in at UCLA, and then you're equipped with such fancy hardwares that you can do a lot of stuff to finally bring the computer vision aspect back to the robotics origin. And then you see a lot of like humanoids and also maybe vision language kind of vision language unification at different robot embodiments. For example, for the Boston Dynamics fancy demo, figure and also Pi 0.5 and also maybe generalist. By the way, they just released the fanciest demo I have seen in 2025. And so now with all those fancy demos, when you look at your unitary, like maybe Go2 or B2, you will wonder when you own your first robot, what will you do, right? So at that time, this was like 2024. We saw maybe back then it was really, I guess, trended area where you plug in VLMs, reasoning capability to all the robot modules. Like there were like, I guess a lot of like such kind of work. So we also tried one of this. And back then we were tackling all the problems about like how to do the closed loop reasoning. For example, if you fail once and then how do you just go back and do retry no matter to the navigation or the manipulation or the grasping pose. And that project worked pretty well on pick and place. And then you kind of want to do like real stuff because back then you can only play with like toys, like toy fruits and also maybe really empty things, empty bottles and all those sorts of it. That's not very useful in my opinion. And then when I was at my office, when I tried to start this project, I asked myself the question, when do we need a robot, like for real? And then you look at all the whiteboards. I have one whiteboard here and you have all the drains on it. And you feel like really, if you have the time to like clean it in time, that would be great, right? And then, so that's when I asked one of my interns and actually my PhD students and say, why don't we just have the B2Z1 setup? Like, let's do the whiteboard wiping and then, immediately after we meet so that you don't have all the drains. They say, okay, that's really simple, right? Because you can collect the data and BLAs are working pretty fine. This is after, I guess, Pi 0's release. And then you have all the data collection set up and they try to teleoperate it. Now, this was an example showing, okay, the data collection was already pretty harsh. So this is actually doing like really slight moves on the wiping, right? And then you also have like really hard moves on the wiping because you cannot control the force. So in the previous case, you have really slight moves, you don't wipe out the drains. And then you have really hard moves. Now you cannot execute the trajectory. So that's making all the, yeah. And then, so basically in this case, we are trying to do like closed loop reasoning. So when you fail, you try to do the reasoning again and try new grasping pose, no navigation positions, and all sorts of stuff. And then this was about the whiteboards when you look at the drains and then want to wipe it in time. Yeah, this was the wiping by blackboard example I'm talking about. So this is moving really slightly on the blackboard using like position-based teleoperation. And also you have really this kind of harsh examples when you have too much force put onto the black whiteboard and then you cannot execute the trajectory. So basically you learn the policy, you get the position, but you're not sure what the force is applied And then no matter whether you learn good trajectories or not, the policy always fails. So that's when we realized that we probably need to have simultaneous position and force modeling to do this kind of counter-reach problems. And yeah, of course, my interns and I was thinking, okay, maybe this is not really difficult because we have all this sorts of like in-hand manipulation that requires dexterity and also tactile sensing. And also this was the content-rich manipulation workshop at ICRA 2025. You have so many fancy demos and maybe fancy skills you can do right now. So how can it be too difficult, right? So I guess in essence, one word that this difficulty is originating from the hardware because you don't have those force sensors on these leg robots. And actually, if you look at the working edition of current adaptive or reaction policies, you have all the force sensors. For example, for the adaptive compliance policy, you have the force torque sensor at the gripper. And then for this reactive diffusion policy, you have tactile sensing on the gripper as well. So force sensing is critical for this kind of behaviors. But for leg robots, you normally don't have it. And then mounting them onto your robot is actually really difficult and costly. And also maybe because there's too many joints on the leg robot itself, it's really difficult to, for example, to propagate one of the force at certain joint to the whole body or the actual joints that are related to this task. So that's like really nightmare back then. And then we tried to look at how we can, I guess those was the major motivation and why we want to do like learning-based force and position estimation without relying on force sensor, because if we can solve this, it will be really easy to just apply to all kinds of leg robots without too much hardware modifications. And then this was I guess the major motivation for this UniFP paper, where we learn a unified policy for position and force control. I guess if we revisit the whole motivation or formulation of this method was like the mass spring damper system we can formulate. So basically you have all the commands of position, velocity, and also acceleration that you desire. You have the actual robot position, velocity, and acceleration. And then this difference can tell you whether you are actually being applied with external forces, right? And then if the end effector moves really slowly in the manipulation scenarios, you can just ignore the velocity and also the acceleration because you are just moving really slowly to the target. And then in this case, it will be really easy for you to both estimate your external force because you know your position, you know your goal, and then you can estimate your force. And also you can know when you are applied with a force, how should your commanded position be adjusted. So that's actually the basic idea about the UniFP formulation. So instead of tracking the position command, we can track the force adapted target X. So this force can be estimated with position offsets is about the upper equation, and then tracking the force adjusted position enables joint force position control. That's basically telling you, I have a position command, and when I'm applying with external force, or I'm trying to apply external force, where should my adjusted position be? Then in those cases, even though you are using a position to control a robot, you are actually commanding your robot to have unified force and position behaviors. Yeah, that's the major trick in our UniFP paper. And then I guess several examples that we can share. For example, the most simplest one, you have position control where you have X target just equal to your X command, and then your end effector will just move along this trajectory. And then also you have, when you have an external force being applied, you can know that your target need to be adjusted according to the equation we just talked about, right? And then if the force is really large, then you should go further and then you will go back. So this is actually the classic impedance control setting where you have X target being calculated as the force adapted position instead of the original one. So when you have a force onto it, it will just follow you. But after you release the force, your X target will gradually go back to X command because there's no this term. And then if you want to do, like, for example, like gravity compensation, force tracking, you can just gradually adapt this command when you are applying the force so that you will track and stay at the position that you are at. So I guess this is the formulation behind this kind of behaviors in our setting. And also, I guess I use this slides to try to give a more concrete intuition on how do we apply a force? Because you cannot say that you are applying like a 30 kilo or 300 Newton force onto something unless you actually lift it up or like push it with with a sensor monitor. Right? So that's actually telling you actively applying a force is actually obtaining the reaction force of the same value. It's not saying, right? So when you have like you want to apply a force. Basically, if I want to lift this dumbbell, then you have the F command, which is just like I'm boasting I have like 300 Newton force applied to the dumbbell. And until you receive this reaction force, you're just talking about this. You're not actually applying the force. So at this balancing state, when you start to receive this reaction force, is when your F command, which is the force command you want to apply, being satisfied. So if we look at this behavior until this rope is straight, and you get the reaction force, before that, your F command will just drive your X target to lift it up. And once it reaches the same amount of value it reaches the same reaction force, you will just stop there at the balanced. And this is how you apply a force, right? So basically, if I say I want to lift this dumbbell, which is probably 2.5 kilos, and then I will just keep going up. Say this is 25 newtons, right, for 2.5 kilo dumbbell, and then I'll just keep going up, and until I receive an external force that modify this term to 0, then I will reach a balance at this stage. So this is actually a demo about this. And also, if you want to have another external force being applied to this force control behavior, you can also move this around, right? Because now we have the balance reaction force equal to force command, and then all the external force, you can just use the zero force tracking kind of scenario to do this. And this will give you the difference between when you don't have the force command, you will just fall down. And then if you have the force command, you will just hold the thing and then do the force tracking or gravity compensation style behavior that you desire to have. Yeah, this is basically about the manipulation. And then if you look back to the mass spring damper system, you actually have more than that. You have the velocity and also the acceleration. And then as we know that for locomotion, we probably don't use the position command. We use the velocity command instead. So if we only care about locomotion, probably we can also like simplify this equation to consider only the velocity differences. And then for the velocity differences, you can have a similar kind of formulation for the desired force adapted velocity, which enables compliant locomotion. So what do I mean by that? So for example, if you are actually just moving forward, if I want to stop you and then you feel the force, in our case, the force adapted velocity will just be 0 because you stopped it, and then you will stop and tilt. And if you don't have this adaptive behavior, then your policy would just keep stepping in place. That meaning that you are still trying to track that velocity, just you can move forward. And if you stop, and then that means that my tracking velocity actually turns to 0. And also for the base force tracking, it's just trying to say it is, I guess it's looking like you are actually having like unitary kind of demo where you just sabotage all the things that you can do all the bad things you can do to a robot. But in this demo, what we are doing is trying to say that if you have a continual force tracking, you will just keep moving forward. So for the COLA paper, we also use some kind of idea about this. And then this was about the manipulation and also the locomotion, which we modeled the end effector position and also the base velocity. So how do we actually learn this force position sampling in simulator? Is basically you have a whole body control kind of RL setting where you train the quadrupeds to let the end effector reach all the position that you can reach. And then you have position command, force command, and also some external force sampled to the end effector. And then you can calculate the desired position target after coping with all the external force and also your applied force. Because in this case, you don't actually need the reaction force. You can just apply a negative or like the reverse direction reaction force directly to simulate the force command. And since you can calculate the real X target, you can just let your robot track the X target with all the inputs like last action, base state, joint state, history. And then I guess the critical thing about our paper is that you can use all the things to actually learn an estimated force to to estimate this external force, so that you can have compliant behaviors or like other behaviors that you desire. And in this case, I guess some details is that for the force sampling, because when you are actually applying a force, you cannot be doing instant addition or like removal, so that we do like a continuous linear scaling about like going up and then going down. And also, this is the force estimation results on the UniFP, where you estimate the force command, and also you measure the actual force being applied, and also you want to see whether your force estimator is estimating correctly. And also, I guess all the things are looking pretty well, but if you actually look at the y-axis, it's within like a 5 Newton range of differences, so you cannot estimate too precise. So imagine you are using at a tabletop, probably for those, for example, like holding an egg, those kind of tasks, you cannot use this kind of force estimation. And then for like, if you're lifting really large weights or like doing all the heavyweight stuff, is pretty, I guess it's enough for doing those kind of tasks. And
Sorry, Baoxiong, I have a quick question. So, in the case of, so you have basically these two more of different commands, like position command and force command.
yeah,
So in the case of you, let's say wiping the whiteboard, right? So you are moving,
yeah,
maybe some kind of locomotion, maybe.
yeah,
But at the same time, you're also applying force, because you need enough force in order to wipe the whiteboard, right?
yeah.
So does it mean that actually the model is able to take in both like force command and position command at the same time, or does these two need to be like switched between?
That's a really good question, because actually, if the force command and the position command are conflicting each other, the robot doesn't know what to do, right? You can imagine one is moving forward, one is holding back. So
Yeah.
in the wiping whiteboard case, you can have orthogonal force applied to the board and then moving parallel to the whiteboard, right? So in this case, you can take both and won't conflict. But in most of the other cases, if you cannot specify the position and force commands correct coordination, then in those cases you need to use, like, for example, position at first and then force directly. So one after another. Yeah.
I imagine like some of these more very dexterous, let's say juggling a ball, let's say humanoid juggling a football.
Yeah.
I imagine it's the human is maybe, I don't know, maybe constantly switching between position command and force command.
Yeah. Yeah.
Yeah. And so but what you're saying is that at least for the current setup, it's you kind of have one of the other, unless they're truly orthogonal. Then I
Yeah.
see. Okay.
So I guess the policy itself, because in the training, we actually consider all scenarios. If there's conflicting force and position commands, we will just let it hold at the position. So theoretically, you can take both commands, but it's just you won't have the desired behaviors, and you won't have those kind of behaviors in real world. I guess like kicking a football will be like a really good case on whether you need to first do position command and then do force command. So we have like a little switch on our controller. So for the blackboard setting, we will first like walk the robot to close to the whiteboard, and then apply force command and position command directly. So basically, in this case, it's orthogonal, right? And then you just continually push that force and then do the left and right wiping. Yeah, so in this case, it's unified. And in other cases, mostly you can just do position or force command, or first position, then force. So this is just like the control modes that we figured out. Yeah.
Got it.
Yeah, it was a really good question, because we had this debate a while ago, because you can only use force commands to do position commands as well. But it's just, in those cases, you cannot be that accurate position. So it was a really good question. And also, you kind of, I was trying to talk about this blackboard setting where you first use position to get close to the drain, and then use force plus position to do the teleop. And then you can control the force so that you don't move too slightly or too harsh on the whiteboard. And I guess how this data contributes to the imitation learning, because you have the estimated force, you have the proprioception, and then your diffusion policy now has the ground truth of our position and force command, because due to our UniFP's nature. And then now your imitation learning policy can not only predict the position, you can also predict the force. And if you pass these outputs to our UniFP policy as a low-level controller, and then you can just directly wipe the whiteboard. So this actually helps with all those, I guess, tasks that requires both position and force command. And this is some examples where you have, first of all, is wiping the whiteboard. And second is just like push to open or push to close kind of door, where you stay at the position, but the force needs to reach a certain amount to let it open or close. And
I'm curious.
we also try.
Got a little bit. So I was still thinking about the last thing, but like instead of predicting position and force, why not just predict like K? Like you have that matrix of gains, right? Like, sorry.
Yeah, it's just for example, I guess you were talking, for example, in the D or the K.
Or D or K, right? Like
so
because like isn't the position
was,
command just like a force one with like really high gains?
We also had a lot of questions about this as well, because if you look about it, this actually considered more like about the robot's whole kinematics, right? Because you can just use forward dynamics and then calculate like even the per joint force maybe. And then
you could have a diagonal.
Because we started from the whole body control kind of setting, so we started with like in this kind of formulation, and D and K here is just hyperparameter, but definitely you can make it more physically meaningful to make sure that the force is more accurate. So we are actually working on this. That's also why I guess there was this big range of estimation variances instead of like doing precise prediction. I guess that's also, if we're talking about this question, and then I guess the more interesting question to ask is like for a floating based robot, and you have multiple contexts maybe, and then so if you don't use this kind of RL kind of simulation, and then if you learn the K, how do you just like use the simulator to learn this? So we were actually trying to figure this out, because for robot arms it's pretty easy, I guess. You can assume like a static base, and then you can calculate all the stuff, and in simulators we can just directly apply the force and read out the positions. But if you want to learn, I guess you can also learn the X. You can also learn the K, but if it's only on the N effector, it will not be that useful maybe, because you need to calculate the aggregated K instead of just the joint, right? Yeah, and also this was the last task about the imitation learning, because now you can think about UniFP as having those kind of tactile kind of feeling, because you can have the force. So with the force amended to the policy, when you have occlusions, for example, if your camera is over here and then you are occluded by the table, you can also do push to open, push to close, because you have the force sensing. So these are the tasks that we selected.
So this is purely force, basically. Basically this completely occluded. The camera can't see anything.
Yeah,
interesting.
But you know the force, right? So this is when the force comes. So this is more like I guess the dexterous hand when you have only tactile sensing instead of visual tactile or like vision, right?
Yeah. So, sorry, Baoxiong, I have a previous question in the previous slide. I'm still don't fully. Yeah. So you the previous slide. So I guess you have 50. Yeah. So you do data collection with estimated forces. So this is your so-called 50 episodes. You go and data collect maybe 50 times, and then And so how do you get the estimated forces again? Is using just now those formula that you have, right? To infer.
Because we learned this estimator during in our simulation,
okay.
So we can have the estimate of this force. Yeah.
Okay, got it. I see. Okay. All right. Okay, then should not.
Yeah, and then it's overall across these 4 tasks is like 39.5 higher success rate compared to the vanilla vision-based diffusion policy.
Yeah, but I imagine even for the human teleoperator, it must be damn tough, because like the human teleoperator don't actually have force sensing, right?
Yeah, so that's also very
the human probably is also failing all the time. Probably also around maybe 70%, 50% success rate. Is it the case?
Yeah. Because you can imagine for the blackboard is or the door is really easy, because you can hear the clicks, right? If you have too much force onto it, like say there's space between the blackboard and maybe a wall, you can tell by that. But beyond that, you don't have the sensing, so that's also a problem. And I guess that's also with the dexterous manipulation, where you need to have those tactile based gloves as well, I guess, to sync the tactile signals.
So what would you say is a rough success rate for the human teleoperator when they're just like trying to open that, the cabinet that have the force close? are they able to do 100% of the time, or they also roughly?
For all these tasks, you can do 100% because it's not that. For example, if you have like a really good marker and then it's easy to wipe and it's not that difficult. It's just that you need to continuously apply that force on the whiteboard. So it will not be that easy, but it will not be that difficult. But for the position only, we'll just normally have those kind of like slight. Sometimes will be
Okay.
What do you think causes the drop? Do you think it's like force estimator error? That's the drop in performance from 100% demo.
Yeah, definitely.
Like, okay.
I guess definitely, yeah.
Okay, that makes sense. So like sim to real transfer issues maybe, or do you think like a real world data set would help? I don't know. Is that
Yeah, I think real world the data sets will definitely help. If you have all the sensors, you can just replace it.
Okay.
Yeah. And also for the simulator, because I guess Chris, great question about the learning the K, because we're actually setting it as a hyperparameter. So the sim to real gap is actually learned we're basically learning this whole thing in the simulator, and without sim to real, you can only rely on the robot to like parameters to sim to real, and you cannot have all those randomizations maybe inside it. And we didn't add this kind of randomization on the KBKDs. And then in this case, the sim to real gap, I guess, will be potentially larger because the force estimated is also in the simulator, and you are trying to have like a real world behavior. Right. So, at my overall feeling about this, if you can have like robots with all the force torque sensors, I'm really satisfied with all those kind of robots. It's just we cannot build them at the current cost. And this is just a demo about like cleaning the whiteboard finally. Yeah, we will just stop. And also you can do a lot of like interesting things with this kind of force position control. And for example, for the tug of war setting, if you just command the robot to have like a resistance force instead of like a compliance behavior, and then you will just do tug of war. And actually we try this game with like, I guess, 3 or 4 girls at our office. As on certain surfaces, they cannot even pull they cannot even win the tug of war. So it's really large forces being applied. And also for the exercising in gym, because I exercise a little bit. So my ultimate goal is to have humanoids working out in the gym. Maybe something in the future. At least
can be a personal trainer, you know.
Yeah, personal trainer. Yeah. And I guess several limitations was like the precise sensing estimation application of force, because we are learning this, and also the modeling itself is only on the end effector or the base velocity. So that definitely, because you're not working on the robot geometry or the kinematics. So that's definitely causing some gap for learning the force estimation, and also the support of different control compliant behaviors. So I guess it's really awesome that you guys already talk about this, because so the second point was talking about in different task settings, we're having different control behaviors. And then sometimes you need position, sometimes you need force. And then for this hierarchical VLA models, so how do you actually like learn this kind of adjustments is really difficult. I guess we still haven't figured out how to cooperate with like a general VLA policy. And also maybe we only mainly tested on separate controls. So this is related to the second drawback, because we are, so for the position commands, force commands, compensation, when do you use what? These are the limitations about the UniFP that we're still trying to work on. And so this comes to the second paper that I'm trying to like give you guys a little bit sense about it. So after you do this UniFP, you win the Coral paper, and then you go back to your home, and then your mom asks, okay, so how does this force and position thing works out, right? And then it's really difficult for you to say, okay, now I have impedance control, I have command control, I have force commands being applied. And then I try to use this as like an example. So for example, if you can do movement tracking and also compliant holding, maybe we can carry something. So that's like a really useful task for like indoor scenarios or like collaboration scenarios. So so before I tried to use this to illustrate to them, they were like, okay, thanks, that's so helpful. And then after I realized this is really important, and then you work out, okay, this is probably going to like human robot collaboration, because you have all the reactions that automatically adjust your pose or like force being applied. And then that comes to the COLA paper, where you have all the collaborating object carrying as a task. Basically, you just use position and force to do lifting, and do the position, which is basically moving around the area.
Why
So
was there
for the
just a
cola,
dead G1? Sorry, this is a distraction. Why is there just like a dead G1 in the background there? Why is it-
yeah, because
Well,
we do a
there-
lot of
there's
like
two of them.
dancing as
That's right.
well.
There are two,
Okay.
man.
We
Because they
have several of
refuse.
them.
Because they are not
Okay.
collaborating with the human. The only one
Yeah.
that's standing up is
Okay.
that's why he's still standing.
Yeah.
Good eyes, Chris.
These are some like veterans for dancing.
Okay.
Yeah. So for learning, learning this object carrying task. So if you only use like the UniFP kind of formulation, you formulate to exact force commands and to exact positions. It's a little bit difficult to specify like under what scenarios do you use what kind of behaviors. Instead of directly modeling the force and position commands, in this case, we try to like look at it from the different perspective where you directly model the task. So basically, in this case, we first learn a whole body controller that lets you to still let your humanoid to reach the position that you want to reach. And then in this collaborative carrying, you apply like a residual teacher to learn when you have a holding thing on your hand, like if this holding thing is having a velocity or like a height, and or like some certain movements in the simulator, what should you do to cope with this kind of change? So this residual teacher is taking the object status as inputs and then using it like reverse on it, like for example the velocity, like the stableness, the holding, like whether you are holding it horizontally or not, like this kind of reward to learn a policy to make sure that your robot is coping with all these changes. And then after you learn this residual teacher, because in real world probably if you don't have the vision, you're not having the velocity of the objects you are carrying, so that's the privileged information, so you distill it into a student policy when you do actual deployment. So in this case, basically we have first of all a whole body controller, and then add object information onto it to learn a residual teacher, and then distill it to a student policy so that you can do collaborative carrying. So in this case, we have several examples of holding like different things, and also maybe walking through different terrains. And I guess this was the most helpful demo I can think of using this collaborative carrying, where you basically truly can work out to collaborate carry something. And also it's really interesting that we had so you had spotted the veteran dancing G1, and this intern we have, he's working on that, and his hand was damaged a little bit.
Gosh.
Because of the calibration of that pattern. So we also see that if we command this robot to like help him, how should we do that? Because he cannot carry. But if you just drag the robot to let it know that, okay, now the object should be moving forward, you can just use that as a signal to tell whether the robot should start moving or not. So this is basically also one thing that you can do with Cola, which is basically, so here he pulls the robot and released his hand, and the robot knows he should be moving, and then he pushed the robot to let the robot know is stopping. Cool. Yes, and then all the takeaways. So this was still under review, I guess. So we didn't have too much technical details released. Some demos and basically a pipeline on how did we do this. I guess the major takeaways that we had was like first of all the offsets between commands and actual robot status during tail force and interaction information. And it's just the position and accuracy still needs to be improved. And also the compliant behaviors are really important in human-robot collaboration for safety considerations. It just, so why I say that coordination with vision inputs are necessary, because we had like some kind of reporter that tried to see what UniFP do and what Cola do, and then he asked, why do you need humanoid collaboration? Why do you just like two humanoids do the collaboration? That is the most. We can just say, okay, we cannot do this with the G1 current D435 kind of camera, and also for the vision tracking, its onboard computation is not good enough. It's not enough, and they are a little bit disappointed. So I guess that's also something needed to be done in the future. And also we have this unified policy that can help VLA type of learning. It's just autonomy only on certain tasks. For example, for the carrying task, we are actually specifying the rewards on the objects or the status of the objects. And if you want to have more fancy tasks or more general tasks, that paradigm is not going to work. So the limitations from UniFP, where you need to figure out all the control modes, is still there, I guess. So for autonomy, for the VLA type of learning, you still need this kind of I guess, the automatic adjustment of force and position commands. So this was because of the talk was given somewhere else. So we also listed some works here. So I guess maybe we don't need to talk about this. It's just recent works about clone, and also maybe how we do VLA, and also how we do like sim to real reconstruction of articulate objects, and then about scene generations. Maybe we can start chatting a little bit about you guys' questions, maybe.
Yeah, I wanted to ask about the VLA. On the VLA side, have you much thought into including this force sensing into, like, how would you incorporate that into the VLA kind of framework? Like, do you think?
I guess first of all, for example, you have the VTAC former. You can directly use the sensing, right? And also maybe this kind of force command. So I guess you can also predict the force commands, I guess, as a external. So for VTAC former, it's still doing the position, right?
Okay. So basically, you think you could add force commands? Do you think that would help with a lot of these VLA generalization tabs? Do you think it would help with generalization, I guess? Do you think it would help like with improving task performance more broadly for VLAs?
I guess for a lot of tasks, I do sense that there's the need for incorporate force sensing at first, and then for the force commands, it's just I guess for commercial robot arms, maybe you can do that with position, maybe because you can just maybe modify the control modes of the arm itself, because the force, the impedance kind of behavior is embedded in the arm itself. So I'm not sure whether you actually need the force command. Maybe the gripper itself, if you push them really closely, you will just have those kind of behavior. But for like robots, I think definitely, yeah.
Yeah, well, I guess I'm just wondering, like, there was Michael had give the example of juggling, where there's like a lot of the actions are very force determined, not position determined, maybe, right? Like there's lots of actions like this that are, so I'm curious as to whether or not, like, we ask this question a lot about how well VLA, how well different models are going to generalize and handle different situations. Curious if it is a better representation for, in your opinion, is it a better representation predicting the force? Like, should everybody be using this kind of thing instead of predicting positions like they currently are, I guess?
Yeah, if I think about it, it is. But the major motivation is just safety. So my overall research plan about this humanoid was like, first of all, you need to have a pre-trained model, and then you have all the real to sim to real kind of stuff to let you fine tune in your home, not any home, right? So you don't have to walk to like work well in every home. You can fine tune in your home, and then in your home you will just need to make sure that it's safe. That's enough, and then I'm okay with like teleoping some data in my home to like let it overfit to my home, I guess.
Yeah, makes sense.
Yeah. I don't because that's why I'm also really impressed with 1x Dabble, because I think that's a really good way to actually collect data and then maybe like do like heterogeneous learning instead of like gradually updating the overall pre-trained policy, and then do separate update on each one's homes.
And that robot is extremely compliant, just naturally, right? Sorry.
Oh yeah. The hardware is unique as well.
Yeah, the tendon.
I think. Yeah, the hardware falling down is probably different from a G1 falling down.
Yeah,
G1 falling down.
I'm super curious.
You do not want to be near the.
You do not want to
like your poor intern who broke his hand, not hurt his hand.
Yeah.
I'm glad he trusts Kola enough that he can use his only remaining hand to.
Now he can only code with his remaining hands. That's really slowing down the whole process. I guess I'm not sure whether this should be talked about, but the actual he put his hand to somewhere near here and do like the MAU calibration, and then he just randomly I don't know what was the situation, but he hurt his arm over there.
Yeah. I have something very similar happen to my colleague when we were doing robotic fighting thing, like but not with G1, with booster T1 actually, but similar thing suddenly gave way and then the finger got snapped. But I mean, yeah, these things are still hard to be around. But I do think that's why I think this is really cool work for especially Cola, where you have really useful work being done here, where human use force to guide the robot to do stuff.
Mm-hmm.
It's almost like a little bit, you can think of it almost like maybe like online RL, almost like, oh, okay, you do it wrongly, I correct you right there. But it's very hard to do, to do a teleop, right? Why don't I just like put your hands, okay, your hands is over here, your hands should be here instead, Yeah. So I think this kind of feedback it's a lot more intuitive for the human, I feel,
Yeah.
to give this.
Well, if you think about it, if you have the vision, you can also do like a cross to let know that it should be stopping. But
I think so. But I mean, in theory, you can show like, okay, this is how you cook the thing. You can show or you can verbalize it. But I think there's also this aspect of like, okay, why don't I just control your hands? It's like, maybe when kids when they're first learning tennis, right? The coach will literally hold the hand of the kid, like the 10-year-old kid. Okay, this is how you hold a tennis racket. This is how you swing. Whether you're learning golf or like there's this part where you do this. Yeah, like.
Right.
The
So
coach
like,
is
this
holding
is
the kid's
kinesthetic
hands.
teaching, right? Like the hands-on
Yes.
kind of guidance while the robot's in gravity comp mode. Like so,
Yeah.
yeah. I mean, I feel like we used to do that quite a lot for industrial robots. Like just teach that this is a like kind of a way to guide trajectories. I'm curious though, like. So there's that mode. There's like teaching it intuitively. I think that makes a ton of sense. Maybe it is like you're saying, Michael. It's really easy to like manipulate the robot, teach it something that way. But do you think you can also use it to make it safer? So like we were talking about injuries. If the robot was always in force control mode, could you make these things actually safe to be in your home? I guess something I think about a lot.
They don't overheat. So long they don't overheat.
Yeah, so like let's set all that aside. Like, did you use UniFP and so on to make the G1 like as it is now actually safe? I guess.
We are actually working on this. There's a similar paper called Soft Mimic. I don't know whether you guys followed on that.
Yep.
We're doing similar things, but still with like a force estimation onto it, because we feel that a force estimation is really important for you guys to use it as no matter for VLA or a downstream task. So only having that behavior is not enough. That's our belief from your UniFP. And I guess for the safety issue, because you can see a lot of like robot arms doing massages all over the world, I guess you can have several modes for the compliance, and maybe the softest one will be safe and it can do its original position. I personally believe that will be not very difficult to solve. And I guess UniFP will definitely help if all the lag robots. And I also believe that if UniFP is equipped with like more force sensors, no matter on the body or on the end effector, it will be great. So in this case, we're using like a tactile included Inspire hand, but not using the tactile. We are only using it for holding. And also there was some error about this Inspire hand, so we cannot grip it firmly. So that's why we had like, some tapes onto it. But if you have the tactile signals as well, I guess that will give you some force signals as supervision for learning as well. But then in those cases, it will be more similar to the dexterous manipulation, where some of the really force sensitive tasks cannot be simulated in the simulator, and then in those cases, probably your force estimator can still not be learned. Yeah, I guess.
Sorry, can you double tap on what you just said? Like you said something about force not being able to learn in simulator. Like, can you elaborate?
Yeah, for example, if you're actually operating a deformable object, so all the force in our setting is basically randomly applying directly to the robot, not from a task, right? And if you have like some deformable object being manipulated, in that process, the task itself will have some certain force behavior. So for example, if I'm like maybe dribbling a ball, and then some of them you need to push really hard, and some of them is just moving down with all the force, not that much. So you will be having a certain pattern for the force being applied during the interaction. And then for that case, if it is like a deformable object, then you don't know what exactly should the force pattern be, right? Yeah.
Yeah. I mean, I guess, I think it's the next natural place for all these models to go. Like nearly everything we do have some kind of force. We take it for granted as humans.
Yeah.
Right.
We're very compliant.
Yeah, we also had this debate about whether you only need several levels of compliance or you actually need the exact force. There is also this debate in our lab as well, because we feel that, for example, there's me feeling that maybe we have a lot of stuff only having like 3 level of harshness on the robot itself is enough. And some of them, for example, doing the dexterous manipulation, they can always think of some tasks that really need really precise force estimation. For example, like cracking an egg, and or maybe even surgical robots. Like in those cases, you definitely really need to be precise. And then for general humanoids, we haven't settled on what's the current. So for the current next step, I still believe that several levels of compliance or like certain compliance behavior will be imported immediately. And then for that precise estimation is in my opinion, probably like 3 to 5 years, or maybe depending on how the field develops.
But I suppose some of this is also hardware constraint, right? So
Yeah.
if we don't have precise enough, and also some of these tasks could be, you need very, very high frequency.
Yeah.
Yeah. If it's just like wiping the whiteboard, you probably don't need very high frequency. But if you're juggling a ball, I think you're talking about maybe 50 millisecond, feedback on the force feedback. I mean, Lionel Messi, he's operating probably like 30 milliseconds, maybe less, 20 millisecond. Those things count, man. I mean, it's a difference between you being a really, really world-class football player versus someone who's like, yeah.
Well, actually, do you guys feel that there will be like robots with all the force sensors incorporated? I mean, just hardware?
I think it'll. My guess is that it would come from like the 1X robot, where it's coming from the tendons, presumably, right?
Tendons?
Like from the actuators. I don't know. Like not explicit. Like I don't know. What do you think, Michael? That's like, I actually like the approach you guys have here, where it's like explicit estimating it from the actuators.
Well, I mean, humans are all tendons based, right? But then we have touch sensor all over our body, so we have that.
Yeah, we have the touch sensors.
So we'd have imprecise moment in theory, more compliant, more safer that way in that sense. But we also have touch sensor all over. So, whereas right now we don't have touch sensors, and then so. You have to.
I bet you could still like crack an egg while wearing a rubber glove, though.
Well, that's the thing. I guess skin and also maybe tendons are different, because they will have like aggregated effects on force sensing. And if you only do e-skins on these robots, you have all the tendons moves. For example, like moving your arm will also have force sensing. That's not desired. So I guess skin and also the actuators, the force sensing from both are maybe, I guess, relevant to the task, and they're different. But we're not sure whether all the hardware companies, whether they're doing this or not.
Yeah. I don't know. There will be some I don't know, maybe pro version, very, very expensive, that at the beginning where all sorts of sensors they can fit in, and then researchers will buy for research reasons. So we will probably have them also at some point. Yeah. Yeah, but anyway, I mean, like, super cool work, Baoxiong. And congrats again on reading the best paper. Very, very impressive work. I actually really like the Kohler work as well. I thought the Kohler is, like, I mean, whatever you're showing now is actually useful.
It's
it is already
compelling.
useful.
Yeah, looks really natural to interact with the robot this way.
We talk about safety from the robots, but honestly, there's another different kind of safety, because, like, some of these tasks, like, for example, if it's very heavy stuff, and like humans, if it's hard labor work, humans do get injured all the time by doing, stacking things. But if it's if now a human actually don't have to do any of the real heavy lifting, just like general guidance, oh, you come here, you go forward to me. Yes, you may risk from, there's a safety concern of the robots dropping on you, but you eliminate a lot of safety issues that, because now we have a robot doing all the heavy lifting stuff.
Yeah.
Which a lot of this workplace injury happened that way, right? Yeah. So I think net is probably more gain than, yeah. Like, I mean, look, if this guy were to, I mean, if these are heavy boxes, I mean, he would have to lift up, from somewhere, and then, if he do it like, like 50 times a day, his back's gonna hurt, man. Yeah, but if you can easily just like, hey, do you want to help me lift up a little bit, roughly force guidance, and it looks like, okay, roughly, this is a place. And then on top of that, give some verbal guidance once you do a VLA. And I think it's very, very useful.
Yeah.
Yeah. So I think this is, very, very good direction.
Thanks.
Yeah. Okay, cool. So I think this is a great place to wrap up. Maybe as a final question, we typically want to ask, like, Baoxiong, like, do you have any cool papers that you come across recently you want to give a shout out to? Doesn't have to be directly related to your work. I mean, you mentioned Short Big just now, but any other paper that you want to give a shout out to that you thought was quite cool?
If you guys can invite some guys from Generalist AI, I was just talking about this with Chris. I do want to know about the harmonic reasoning kind of setup.
Yeah.
We'll do our best.
Okay, Chris, let's work on that.
Let's try it.
We'll do our best. Yeah, let's try.
Yeah, that would
yeah.
be great.
Yeah, anyone listening in, if you know the guys or you are from journalists, my DM and Chris DM is open. Yeah, pretty cool. Yeah, do they have a paper of some sort? I don't know.
They have a
I
blog
just woke up.
post just came
They have a
out.
blog.
Oh, they have
Yeah.
a blog post.
Yeah.
Oh, okay, got it. Yeah, that if I'm not wrong, it's all UMI type of data, right? It's like yeah.
Yeah.
They've got more really cool videos.
That would be very interesting. Yep.
Some new harmonic reasoning. Yeah. Well.
Yeah. Cool. All right, cool. Okay, that's a tall order, but we'll try.
Yeah. Luck.
Yeah. Okay. Cool. Any other paper that's maybe a bit easier to guess? I don't know. Like, okay, cool. If it's that, we'll try. All right. Okay. Anyway, thank you so much for the time, Baoxiong. Really fascinating work. And I, this is I think the second or third time someone from Big AI Group, coming on the pod. Thanks for doing your work. Thanks for open sourcing. Writing all this paper. Really helps the community to.
Yeah. Thank you guys for
the whole field.
the podcast. Yeah, we'll keep doing this effort and try to make it more useful.
Yeah. Awesome.
Thanks.
Awesome.
Awesome
Cool.
work.
Well, I'm sure we'll have you again soon.
Yeah.
Yeah. Your next one. All right. Cool.
Yeah.
All right. Have a good one then. All right. Until next time. All right. Ciao.